Hello, welcome to the second video on custom IP design for Vivado. In the first video, we saw how to design a FIFO write controller FSM and simulate it in the Vivado design environment. In this video, we will see how to convert this FIFO controller to a Vivado custom IP. So first we will go through the process of converting this model, this RTL model that we have created, into a Vivado custom IP. The next step will be to use this custom IP as part of a Vivado block design. So in the second step, what we will do is we will integrate this custom IP with a FIFO that is available in the Vivado IP design repository. So we will create a block design of which the custom IP that we have created is one of the components. The other component in the block design will be a FIFO that is picked up from the IP repository provided by the Vivado block design environment. In the third part of the video, we will write a test bench for verifying this FIFO system. So that will be the agenda for this presentation. The first part will be making a custom IP out of the controller that we have already created. So you can see that we are residing in the same project which was used for creating the controller, then writing the test bench, and finally simulation of the controller and synthesis of the controller. So these are the tasks that we carried out in the first part of this presentation. Now we need to use the custom IP features provided in Vivado for making a custom IP block out of this controller. So we'll go to this tools option and you can see that there is a create and package IP option that is provided. So we'll click on it and it asks you whether to package the current project. So this is a default option called include XCI files. We can use the default. I'm not going into the details of this at this stage. Okay, now the custom IP block has been created. So we will have to add certain information pertaining to this custom IP block. The first one is of course identification. So you can specify how this block will be identified when it is used as part of a block design. We can also add the name of the person who has created this block. So if you want to change the name that will be displayed when this block is used in a design, you can use this edit option. And if you are part of a company, you can add the company URL also. The second part is compatibility. So Since while creating the project I had added the basis board, the Arctic 7 FPGA is already displayed as being compatible to the design. So if you want any other FPGAs to be added, you can use the add option. Then you can go to the ports and interfaces section, which will list out all the ports in this design. So we are familiar with the ports that are part of this controller. You have the do rightward port, which is an input port that triggers the entire write transaction. Then you have another input port which is expected to be driven from the FIFO, that is the FIFO full, and two outputs, the write enable, which will connect to the FIFO write enable, and the write error, that will be a status signal that will go to the host in, and this particular status signal is supposed to be asserted if there is a failed write transaction. So if you go to this customization GUI, you can see the custom IP that we have created in the block form as it would appear in the block design environment. So now the custom IP is shown here as a block with all the peripheral pins. Therefore, once you are done with this packaging steps, you can finalize the creation of the custom IP by clicking on this package IP button. Now the IP creation process is complete. So just to verify whether this IP is part of the IP has been made part of the repository, we'll again go to flow, and we'll open the block design environment. We'll open the block design environment. So the block design project space is now open. Just to see whether the custom IP is already added, we can use this add IP option and do a search with the keyword FIFO. So there are so many blocks related to the FIFO that are appearing. You have different types of FIFOs, and you can also see an AXI virtual FIFO controller, which I had briefly mentioned in the first video. This is a built-in FIFO controller provided by Vivado. Then you have the Fifo Generator, which we will be using for verifying the custom IP. The Fifo Generator, as the name implies, it is a block which is a customizable FIFO. So when we include this block as part of a block design, we can instantiate a FIFO whose parameters can be set by the user. We'll see more about this in the next part of this video when we will be doing a block design. And finally, the last block that is appearing is the custom IP that we have created. So you can see that the custom IP creation is successful, and the IP is now available as part of the Vivado repository. The next step is to create a block design using the custom IP that we have already created, that is the custom FIFO write controller that we have already created, and a FIFO that is picked up from the Vivado IP design repository. For creating a block design, we will use the create block design option, which will open up a block design environment in your project. So you can see that we are residing in the same project in which we created the custom IP. When you right click on this space, the set of IPs that are available in the block design environment will be displayed. So we'll use the Fifo keyword to locate the IPs that are available uh, related to the Fifo. As we had seen earlier, several IPs are listed, of which the last is the custom IP that we have created. So now we have instantiated the custom IP in the block design. The next step is to pull down the built-in Fifo that is available in the Vivado repository. So for using a Fifo, for making a Fifo part of your block design, you have to use the Fifo Generator IP that is provided. The Fifo Generator is a block which can be used for generating a Fifo having a desired set of features. For configuring the properties of the Fifo, we have to double click on the IP block. This will open the properties window where there are a lot of options that are given to the designer, starting from the basic options, the native ports, the status flags, the data counts, and so on. We will not go into the details of all these options. I will just configure the bare minimum that is required for using the Fifo. So here there are three different interfaces that are listed, which you can choose. The first one is a native interface, which means a simple Fifo interface. The other two are related to the AXI bus interface. The AXI bus is the interface bus that is part of the AMBA bus standard. The AMBA bus standard is a on-chip interface bus that is provided by ARM. This bus can be used for interfacing various peripherals to a host, and it is provided as an IP in Vivado. So in the block design environment, you have an option of using any block with a native interface, that is a basic interface of the block, or the AXI bus interface. So here we will choose the native interface for the Fifo. That means all the pins of the Fifo will be used as such. We will not be providing any wrapper which will be compatible to the AXI interface standard. And the other options, we will just leave the default option like the common clock, block RAM, and so forth. Coming to the native ports, again you have two options, the standard Fifo and first word fall through. We will use the standard Fifo option. We will configure the write width to 8 bits. Write width basically allows you to specify the word size of the Fifo, and the write depth to the minimum number of words, which is 16. Now the Fifo that we are going to use is configured to have a word size of 8 bits and a depth of 16 words. Now if you go down a little bit further, you can see some initialization option. So that lets you specify the type of reset for the Fifo that you want. So you can choose between synchronous and asynchronous reset. So let me choose asynchronous reset. And for the full flag, you can choose whether the reset value, that is the default value, is 1 or 0. So let me make it 0 because I have designed the controller assuming that the active state, the active level of the full flag is 1, which means that when the full flag is asserted, it will have a level of logic 1. Therefore, I am configuring the reset value of the full flag as logic 0. And there is one more option that is provided, that is the dout reset value. So dout is the data bus through which a data that is read from the FIFO will be made available. When the FIFO is reset, the dout will have a reset value. So here by default, the reset value for the dout bus is 0, which we will retain as such. So that completes the configuration of the FIFO. Of course, there are so many other features which we will not go into. There you are. The FIFO is now ready for being used as a block in the block design. Now we will start interconnecting the various pins. We will first connect the clock pin because both the modules are going to be driven by the same clock, and we will declare this pin as an input pin. For declaring a particular pin as an input or output port, you can right click on that pin and use the create port option. So this lets you declare a particular pin as a port and specify its direction and the name that is to be used when the port is used in the periphery. You can see that now the clock pin is declared as an input port. Now we have two reset pins, one for the controller and one for the FIFO. We are not going to connect them together because the nature of the reset pins, the nature of the reset inputs in the controller and the FIFO are different. We have designed the controller such that it is having an active high reset, whereas the Fifo generator has an active low reset. You can get the details of the Fifo generator reset from the data sheet, which is provided by Xilinx. Hence, we will not connect the reset pins and use a common reset. We will use separate ports for resetting the controller and resetting the FIFO. So the controller reset will be declared as a separate port, separate input port, and the FIFO reset on the other hand will be declared as another port. So there are two resets which are part of the design. The first one is the controller reset, which is named as RST, and then there is the FIFO reset, which is named as RST_1. Now there are two inputs to the controller, full and do write word. Do write word is the input which is supposed to be driven by the host, of which the FIFO controller is going to be a peripheral. In our simulation, we will be driving this pin from the test bench. We will declare this input, we will declare this port as an input port. Now coming to the full input of the controller, this input will be driven from the FIFO. It will be driven by the FIFO full status output. So where is the FIFO full status output? In the Fifo generator. You can see that there are two groups. These two, FIFO_write and FIFO_read, they don't signify ports in the design. They are a group of ports which can be seen by simply collapsing the group. So the FIFO write group consists of the FIFO full status output, the data input bus, the 8-bit data input bus, and the write enable control signal into the FIFO. We will connect the FIFO full output to the FIFO full input of the write controller. The data input bus of the FIFO is an 8-bit input which will be controlled through the test bench in our simulation. Therefore, we will declare it as an input port. Then in the write port group, there is the write enable, which is the control signal that is used for writing a word into the FIFO. When this signal is asserted, a word will be written into the FIFO. So in our case, this pin will be driven from the WN out of the FIFO controller. We have designed the FIFO controller in such a way that whenever there is a 0 to 1 transition in the do write word input, the controller will generate the write enable for a single clock, which means that this controller initiates a single word write transaction into the FIFO. Now we have the W error out, which is a status signal from the controller that indicates a failed write transaction. This is actually supposed to be read by the host. In the simulation, we will be reading this pin from the test bench. So we will have to create a port for this purpose, and the W error out will be declared as an output port. Now we have the FIFO read port group, which consists of the empty status output, the dout data bus, and the read enable control signal. The empty is a status output from the FIFO, which is asserted when the FIFO is empty. That means there are no words that can be read from the FIFO. All the words have been read from the FIFO. So this will be declared as an output port, which we will read from the test bench. Then there is the data out bus, which will provide the data word that is read from the FIFO. Whenever there is a read operation in the FIFO, the data that is read out of the FIFO will be made available through the data out bus. So we have designed the custom IP FIFO write controller only for a write transaction. So the controller is not capable of a read transaction, but during simulation we will be doing a read transaction that will be initiated from the test bench. Hence we will declare this bus as an output port that will be directly read by the test bench. That leaves us with one more status signal, one more control signal, that is the read enable control signal, which will also be controlled from the test bench. Therefore, we will declare this as an input port. Now we are done with all the interconnections. So we have created a very simple FIFO system that consists of the write controller FSM or the custom IP that we have created, and the FIFO that is instantiated from the block design repository. Now we are ready for simulating this design, but before that, of course, there are a few steps that we need to carry out. The first one is we will validate this design by right clicking on the design and clicking validate design. This is basically intended for determining whether there are any errors in the interconnections. For example, you are supposed to connect the output port of a particular block only to the input port of another block. So if there are any such inconsistencies or connection errors in the block design, they will be identified during the validate design phase. Before proceeding further, we will use the regenerate layout option just for cleaning up the layout. Now you can see that the layout is much more, it has a much more cleaner, orderly appearance. Our objective now is to simulate this particular design. But for simulating this design, we need to write a test bench. And if we need to write a test bench, we want an HDL description of the top level design that we have created. For that, we will move to the project window and we will click on design sources. Sorry, we will not click on design sources. We will be clicking on the design that we have created, which is design underscore 1. That is the block design. That is the name of the block design that we have created. So when you right click on this block, among several options that are shown, you have the create HDL wrapper option. When you choose this option, an HDL file that describes the top level design that you have created will be generated. So let us click on this option. You can see that an HDL file which is called design underscore 1 underscore wrapper is created. Let us just double click on this file. Sorry, let us just right click on the file. So when you open this file, you can see the top level design that we have created. Before proceeding further with the test bench, we will just verify whether the design is in order from the point of view of synthesizability. So we'll just run a synthesis in this design. So you can see that there are no issues with the synthesis. Therefore, we are ready for simulating the design. For simulation, we have to add a test bench as the simulation source. I have already created a test bench for simulating the top level design, design underscore 1 underscore wrapper. So now I will add this test bench as a simulation source. So again, we go to add sources and add this file as a simulation source. So it is available in the home directory of the project. Now the test bench has been added to the project. We will take a look at the test bench code. By opening the source file. All the control inputs and the global inputs like reset underscore 1, all these inputs are initialized to their default values, as you can see here. The data input to the FIFO has been initialized with the value decimal 85, which is the decimal equivalent of 55 hex. In the initial block, I am applying a short reset pulse in both the reset inputs. The RST input, which is the reset input for the FIFO controller, and the RST underscore input, RST underscore 1 input, which is the reset input for the FIFO. You can see that the reset inputs are having complementary values because the reset input to the FIFO is an active low reset. So that's why we had two reset ports in the first place. Then of course we have the always block which generates the free running clock. This has been already explained in the first video on the FIFO controller. Beneath this block, the free running clock generation block, you can see two blocks of code, out of which one has been commented out. The first block of code pertains to the simulation of a single write operation in the FIFO. So I am using a register variable called int just for keeping track of the number of clocks and timing the assertion of the control signals. I am asserting the do write word input signal after leaving out sufficient gap from the assertion of the reset. I am leaving sufficient number of clocks before asserting the do write word control signal. And after asserting the signal, I am just leaving it at that. I am not bringing it back to 0, which means that there is just a single 0 to 1 transition. And we know that the FIFO controller basically looks for a 0 to 1 transition in the do write word input. So when there is a single 0 to 1 transition, you can expect just a single write operation to happen in the FIFO. And notice one more thing. The assignment in the test bench for the control signal is done using a non-blocking assignment operator. This is very important. Whenever you are assigning control signals under an always block in a test bench, please ensure that if they are synchronized inputs, they have to be assigned using the non-blocking assignment operator. So that pretty much sums up the test bench. This block of the test bench, we have commented out the other block. We'll simulate the other block later. So the first block basically is concerned with simulating a single write operation in the FIFO. So let us see how it simulates in the block design environment. So the file has been already added to the project. Now it is just going to the simulation window. So now we will run the simulation and observe how the write operation unfolds in the actual FIFO environment. So this is the waveform window for the simulation. Let us take a closer look to figure out what has happened. I think it is zoomed out. So you can see the resets here, the reset to the FIFO controller as well as the reset to the FIFO. And after leaving out sufficient delays between the clocks, I am asserting the do write word input at this point. So this is the point at which the do write word input is getting asserted. And we expect a write operation to be triggered by this particular event. So how to find out? How to find out if a valid write has occurred? One option, one means by which we can do this is to look at the empty status signal of the FIFO. You can see that the empty is asserted in the beginning. It remains asserted till the do write word is triggered, and when the do write word operation is triggered, you can see that after 2 clocks, the empty status is deasserted exactly for 1 clock interval, and then again it reverts to its default value of 1. So what really happens? We can also take a look at the data out bus in the FIFO. As I had mentioned earlier, the data out bus is concerned with a FIFO read operation. Whenever a FIFO is read from, the word that is read from the FIFO is made available through the data out output bus. The reset value of this output is 0, as we had seen in the block design phase. The reset value is 0. And you can see that at this point, the data in this bus changes from 0 to 55 hex. And 55 hex is nothing but the data that we have provided in the data in bus. So it is evident that the data 55 hex, which was driven at the input bus of the FIFO, is now available at the read output of the FIFO. We have kept the read enable asserted throughout the simulation. So it means that the moment some data is available in the FIFO, it will be read out. In this case, we have just written one data into the FIFO. The value of the data that is written is 55 hex as indicated by the D in input data bus. And after the write operation, the empty is deasserted. And at the very next clock, you can see that since the read enable is asserted, the data is immediately read out. And when the data is read out, the empty signal is again asserted, because there was only one data available in the FIFO, and since this data also has been read out, the FIFO goes back to its empty status. So from these signals, from these ports, it is evident that a write operation has taken place. Now, just to make sure that the control signals are behaving as expected, we will go down the hierarchy. We will go down the hierarchy, and we will also monitor the control signals that are generated by the FIFO controller and also the full status output of the FIFO. For that, we will go back to the project. We will have to choose the simulation objects. So this particular window, the simulation object window, lists out all the modules that are part of the simulation, starting right from the top level, which is the TB underscore design underscore 1 underscore wrapper. That is the test bench module. Then you have all the devices under test, the block design D1 rather, and the modules which are part of this block design, that is the FIFO and the FIFO write controller. So when you click on the FIFO write controller, you can see all the ports of the FIFO write controller, and we are specifically interested in the full status signal and the write enable out signal. We just want to see whether these signals are behaving as expected. Of course, we have established that a successful write has already occurred in the FIFO. Just to make sure that the behavior of the controller is along expected lines, we will also add these two signals to the waveform window. So I have added these two signals to the waveform window, and now I will repeat the simulation. I will repeat the same simulation, but with two more signals added to the waveform window. So we'll just save the waveform file and go ahead with the simulation. So we are simulating the same test bench, but with the difference that we have added two more signals from the Fifo write controller, just to doubly verify that the control signals are being asserted as expected. So now we have the full and write enable out status signals also available in the simulation. So let us slightly zoom the window. So you have the do write word control input signal being asserted at this point, at this clock. And as expected, since the Fifo full is 0, that means the Fifo is not full, the Fifo controller is now triggering a write operation into the Fifo by asserting the write enable output. And we know that this output is connected to the write enable input of the Fifo. So when this input to the Fifo is pulsed, it will trigger a write operation. And quite expectedly, you can see that at the very next clock, the empty signal, which was initially 1, is now getting deasserted. This indicates that the Fifo is no longer empty. Now, since we have kept the read enable asserted for the entire simulation, as I mentioned earlier, the moment the Fifo is not empty, at the very next clock, the only word that has been written into the Fifo is now read out, as indicated by the data 55, which is being made available at the dout bus. And when this single word has been read out, the empty signal now again is asserted, which indicates that once again the Fifo is empty. So this simple test bench is used for verifying whether the Fifo controller is able to successfully initiate a write into the Fifo when the Fifo is not full. Now we will simulate multiple writes into the Fifo. We will write words sequentially into the Fifo until the Fifo is full. And subsequently, we will initiate a series of reads from the Fifo till the Fifo is empty. So we will use the same test bench, but we will comment out the first part of the code that pertains to the single write operation. You can see that now I have uncommented the second part of the test bench, which basically creates a series of writes, a series of write transactions into the Fifo. For this particular simulation, I have introduced some modifications in the initialization of the control signals. You can see that I have now restored the read enable to its reset value, that is 0. Initially, when we simulated the single write, you may recall that we had kept the read enable asserted for the entire duration of the simulation. But here, in the initial phase, I am keeping the read enable deasserted. And another change which I have introduced is related to the write data bus din. So I have initialized din to 0. Earlier you may recall that we had initialized din to 55 hex and we had left it unchanged. for the entire simulation. But here I am initializing D into 0. Now coming to the actual transaction, you can see that I am toggling the do rightward control input. After leaving out a few clocks following the reset, I am continuously toggling the do rightward input, and the index used here is chosen such that we toggle this to initiate exactly 16 writes into the FIFO. We know that we have configured the FIFO for a depth of 16 words. So in this particular simulation, we will write 16 words into the FIFO such that the FIFO becomes full. And the data input bus, which provides the data word to be written into the FIFO, is also modified at every clock edge. We are not keeping the data input bus constant as in the previous transaction. We are changing it at every clock. The reason for doing this is to verify whether the same data that is written into the FIFO is being read out. After the write operation, as you can see here, we will initiate a series of reads from the FIFO. Again, I am leaving out sufficient gap between the write and the read. I am not overlapping the read and write operations. I am initiating the read only after all the FIFO locations have been written into. Again, this is to just show you how the FIFO is read in a sequential fashion. So after leaving out a gap of a few clocks following the write, I am triggering a series of reads from the FIFO, and we can verify that the same data that is written into the FIFO is being read out in a first in first out fashion as expected. So this is the series of tasks that we expect to verify using this particular test bench. So now we will go ahead with the simulation. So we will analyze the write phase and the read phase separately. We will start with the do rightward input. You can see that I am toggling the do rightward signal repeatedly because we know that the write operation into the FIFO can be triggered only by a 0 to 1 transition. So if we want multiple write transactions into the FIFO, we cannot hold the do rightward input high for a series of clocks. Unless we repeatedly toggle this particular input, multiple writes cannot be carried out into the FIFO. So when the do rightward signal is toggled, you can see that the write enable into the FIFO is also pulsed. So for every toggle of the do rightward input, there is a single clock interval pulse that is generated through the write enable output, and this is done by the FIFO controller. So for every pulsing of the write enable, a data will be a data word will be written into the FIFO. So when the first write enable pulse is generated, the data 1A will get written into the FIFO. And for the second pulse, the data 1C will get written into the FIFO. You can see that the write enable is not kept continuously asserted because basically we have done the FIFO controller for a single write transaction. So here we are creating multiple writes by repeatedly toggling the do write word. You can also keep the write enable asserted for uh, carrying out multiple writes into the FIFO. But here, of course, we have built the controller in such a way that at one go, only one write transaction is possible. So for multiple write transactions, we are repeatedly toggling the write enable signal. So this process continues for 16 words. So for the 16th time, when the write enable is asserted, as you can see here, the word 38, the word 38 hex will get written into the FIFO. And that is the last write into the FIFO because we have configured the FIFO for a depth of 16 words. Therefore, following this write operation, the full signal is getting asserted, which indicates that you can no longer write any more words into the FIFO. Now we look at what happens while the FIFO is being read from. As you can see, after leaving out a few clocks, following the completion of the write, I am asserting the read enable signal. And once asserted, I am just holding it asserted for the rest of the simulation. And let us see what happens. So the read enable signal is asserted at this clock. And we know that the first word to be written into the FIFO was 1A hex. So in keeping in line with the behavior of the FIFO, the first word that was written is now being read out at the next clock. And all the subsequent words, 1C, 1E, and so on, till the last word, that is 38 hex, which was written into the FIFO, are being read out one after the other. And when the last word is read out, you can see that the empty signal is asserted. So when the last word 38 hex is read out through the dout data bus of the FIFO, you can see that the empty signal is being asserted. So now we have verified the FIFO for a complete set of writes, and correspondingly we have read out all the words. So we have written into the FIFO till the FIFO is full, and then we have triggered a series of reads from the FIFO, and we have verified that the words written into the FIFO are those that are being read out. So this completes the simulation of the FIFO system. Therefore, to summarize, we started with creating a custom IP out of the FIFO controller that we had created in the previous video. The next step was to realize a block design with this custom IP as one of the blocks, and also by adding a FIFO from the Vivado block design repository. So that was the second part. And in the third part, we have simulated this FIFO system for two different transactions. The first one being a single write and a single read, and the second one a series of writes into the FIFO until the FIFO is full, followed by a series of reads from the FIFO till the FIFO is empty. So with this, we complete the second part of the video on custom IP creation, design, and simulation. Thank you.